great pleasure to introduce Denis Brunet, who is a technical staff scientist at the CIBM EEG HUG-UNIGE section. Denis will be presenting EEG source localization in the Cartool toolbox, solving a single subject case. Thank you, Denis. The floor is yours.
We talk about EEG source localization, which has both theoretical and practical challenges. And fortunately, the theoretical parts are very well covered in a lot of articles. But unfortunately, many of the practical aspects are just assumed to be solved and fixed, and nothing to be done. And also, unfortunately, these practical problems that we have with a single subject is very sensitive with specific subject or patients. So today I'm going to address 4 of these real-life issues. Basically, the MRI realignment, which we need for the inverse solution, for the EEG source localization, the electrodes co-registration on the head, and the solution space balancing, where are the points we are going to have solutions in the brain, and a little more technical thing about the skull thickness estimate that we need for the models. So these are the four points I'm going to address today. Let's talk about the context. So we talk about high density EEG. What is a high density is like above 64 electrodes. Currently at the lab, we're working with 257 electrodes. It could be 129 or something like that, but more than 64. We can do quite a lot of things when we have enough electrodes. One thing, for example, is topographic analysis, where you look at the whole brain, the whole EEG as a template. Or another thing we can do is EEG source localization. You can recompute what's inside the brain. And that's the talk about today. So EEG source localization from high density EEG. The other thing I'm going to use a lot is I'm going to talk about the Cartool toolbox that we developed at the lab since 1996 already. So it's about 24 years development. So what's the idea of this toolbox is we still have people working separately on their own method. They develop their own toolboxes. And at one point, we need to group them into a single package. So what I do, I just rewrite the toolbox that existed from different people. I rewrite them in C++ and put them into Cartool, the toolbox. Once it's done, you can redistribute it to other people. Historically speaking, the reason for Cartool is also that, for example, many people from the hospital, so physicians, have to use it. And so you need something like with a user interface, which hides the unnecessary complexity. So you don't want to expose all the parameters of equations. That's really useless and confusing. So you want to hide what is not really needed for the user. At the same time, you want to still expose what are the critical parameters. So what is really important for the user. And again, everything is wrapped into a user interface and user interaction, which is a key in Cartool. By the way, we have 2 articles on the Cartool toolbox, one from 2011 and another one like last year, 2019. Okay, that was the intro. Now let's step into what's called the forward and inverse problem, a small recap. The forward solution is basically how physics works. So you've got sources in the brain, electromagnetic sources, and then the signal goes through some layers of media, up until the electrodes where they get recorded. We record the electrical part, of course. And that's what we got on the surface. You've got the EEG. The inverse solution, or EEG source localization, but very often I talk about inverse solution, is the other way around. So we go from the EEG on the surface and we go back to estimate what were the sources inside the brain given the configuration on the surface. So that's the inverse. So the forward solution is twofold, and one part is geometrical, and that's kind of the focus of today. Geometrical in the sense that what we are interested in is the geometrical relationship between a source here and the electrodes, how the signal will spread to the surface electrodes. And here I show two real-life subjects. On the left, a male, on the right, a female. Doesn't really matter, but what you will see is that you can see already that the shape of the skull, the shape of the brain is totally different, which means that the relationship between every dipoles within the brain and the electrodes is kind of really different. The star, for example, is basically in the visual cortex here, and you can see that it will spread much differently on the electrodes according to the geometry on the left and the right. So there's a geometrical part, how sources relate to the electrodes, and there is an electromagnetic part. For example, that's a single medium with a single dipole equations. And actually, that's not the talk of today. What I'm really interested in right now is the nitty-gritty, the really concrete part of the geometrical part of the problem, not the electromagnetic part, which is well covered. It's electromagnetic equations. So I'm interested in this part, the geometry. And more specifically, the guideline for today is about the subject. So what are the real problems with real life MRIs, real life electrodes, what's happening, how we can solve that? Because very often the templates are already nicely pre-processed, of course, so there is no issue basically with the templates. The problems with the subjects, or more specifically with patients from the hospital. Okay, so we're about to talk about EEG inverse solution. And to make it work, we have to solve what's inside this weirdly shaped box here. So basically that's resolving some geometrical problem with the MRI. So I call that pre-processing the MRI in the idea of the inverse solution. How can we co-register the electrodes on this MRI? And the forward solution, so the electromagnetic part is not covered. I'm not talking about that. What I'm going to talk is about where to put the solution space, where are the points with the solution that we're going to retrieve. And another problem that we face is we need some skull estimate for the process of the forward solution. So I've got these four things: MRI preprocessing, XYZ, the electrodes preprocessing, solution space, and skull thickness. That was a bit long intro, but so now we can jump into the water. So MRI, again, I'm not talking about general MRI preprocessing. I'm just focusing on what we need for the inverse solution in our specific case of subjects preprocessing. Okay, what we've got as input as day-to-day cartoolers have some input. Very often it's MRIs from hospital, and if you got lucky, you got the full head. If you got unlucky, you got the head is cropped like at the nose level. Even the cerebellum is cut out. So you've got like a very narrow part of the head, and you still want the inverse solution to work, and that's a bit challenging to say the least. And we're not talking about noisy MRIs like old MRIs. It's not like Rolls-Royce MRIs that you've got you guys around here. It's like very corrupted MRIs. Axis orientation can be anything, and the alignment can be really messy. When I'm talking about alignment, is that patients very often can have like a bandage, or they got an operation somewhere on the skull. So when you position them into the MRI, you get the problem that maybe the head is tilted, and you cannot work around that because that's a patient. And of course, the classical bias field problem, but that's not specific in our case. The output, what we want for the inverse solution, while you want a nice MNI space orientation, it would be even nicer to have the center into the anterior commissure. The really important thing is that you really want to have the mid-sagittal plane aligned correctly. So that's really need to be right in the middle of the brain. Again, because patients usually don't have that. Yes, so a good MNI transverse plane also is nice. And we need the bias field correction. So there is a toolbox. This is a quick snapshot of the MRI pre-processing toolbox in Cartool. Actually, the preset is about, yeah, that's what we want, inverse matrices, full head pre-processing. But let's not focus on the whole thing. What I was in yellow, what I was focusing on is that these two options are here. We want to realign the mid-sagittal plane. That's really important for us. I don't know. Ah, yes, I can have the laser. So I want to have the mid-sagittal plane realigned. So that means the plane going through the brain. And also it would be nice to have a nice MNI transverse plane. So this plane aligned. Let's have a look at some real life examples. So that's on the left, that's the real MRI that somebody gave me. So that's a physician gave me that. So you can, I did not need to blur the face. You see that the MRI is totally corrupted. So everything on the bottom part is like, I don't know, looks like the head has been removed from the body. And it's a lot, there is a lot of noise, there is a lot of bias field. After the pre-processing, this is what we have. So there is the mid-sagittal plane realigned, the MNI transverse plane, and it has nicely found the AC, the anterior commissure, and put the origin right here. So we kind of in a pseudo MNI space here. We're still in the patient space, but we are realigned like the MNI. So that's a real life. It was like a very, very difficult to have the toolbox work on that. That's another patient. And you can see that, yeah, there is something problematic with the brain. But still, we can make it work. Basically, what didn't work, of course, is the AC, the anterior commissure automatic detection. Didn't work, but that's not surprising in our case. Another real-life example is a cropped MRI. So we can see everything is missing. We don't have the jaws, we don't have the nose, we don't have just the bare part of the brain, and we still want to have the inverse solution for this guy. That's the pre-processed. Another real-life example, which is, as I say, that's a patient which certainly was operated, and on the MRI, the head was tilted. That's what we want at the end. And more precisely, if we can bring some focus right here, is that the mid-sagittal plane, so the cutting plane here in the middle, has to go through the brain. It's not going through the face or the head itself. What we want is to cut into the left and the right part of the brain, which it did actually. It did nicely, but we can see that the brain is not symmetrical between the right and the left. Okay, so that was the MRI. Now the electrodes co-registration. I will go maybe a little faster. We can have as an input any electrode coordinates. Again, that can be whatever the manufacturer will set. The geometry of the electrodes could be like also anything. The worst of case is like the electrodes are spherical, which you can guess is not very anatomic, to say the least. But we have to work with spherical electrodes for some time. It can be like any approximate geometry. It can be a template, or it can be like realistic stuff like measured from the patient. Again, we want something realigned, but the most important thing here is that we want, of course, the electrodes to be co-registered on the head. So we want them to really fit on the head correctly, so we can have the right geometry, as I was talking at the introduction. So there is the toolbox for that is while creating inverse solution, but yes, doesn't matter. Just some examples of spherical electrodes. Again, that's not anatomical. We have problems with that. We can have templates like, what's that, 348 electrodes from which we can pick specific electrodes if you don't have the right patient's electrodes position. On the left here is a template that we made here in Geneva. And on the right is a real life measurement of somebody, of a subject. And here is an example of what you can do with the package. You can take, for example, this spherical electrodes, and after the package pre-processing, this exact spherical electrodes can be back projected on the real life head. So this is the electrodes as input, this is the output. So even if the worst case is the spherical electrodes, we can find a way to work around. Of course, the best way is to have, for example, in these two guys, we start with the template electrodes, and it's easier to fit on the real head. Oh, what do we have here? We also have some monkeys, because we also use the toolbox on rhesus macaque, and we also made the prototype on the mouse. Of course, the electrodes are very tiny set of electrodes. It's a grid on top of the mouse head. So we can use the same package, and we can use the same toolbox to co-register this very special case. So a monkey on the left and a rat or mouse on the right. The solution space. What I talk about solution space is where we are going to have the inverse solution, where we are going to have the estimates of the localization. We used to have like we used to have problems with this solution space. Basically, we have a downsampling aliasing, because basically the solution space is downsampling the brain, and every downsampling has you need to have some you need to be careful when you downsample. You have to be very careful to balance between the left and the right solution points. And I'm just going to show a few examples. And also what we want in our specific case of inverse solution, we also wish that every solution point in the brain have at least, if memory helps, I think 6 neighbors. So you need a minimum of neighbors for each solution point. Said otherwise, you just drop the isolated point. So look at some very ugly inverse spaces, and This is actually our toolbox. I mean, very long ago, it was an intermediate stage, but just to showcase what is a bad distribution of solution points. So here you can see that there are lots of holes. So this part of the brain is not covered. This part of the brain is not covered, and it's not really symmetrical. That's the same bad example. And you can see, for example, around the mid-sagittal plane, that there are a lot of solution points on the right and none on the left. And that means there will be no solution here on the left part of the brain, which of course is a problematic. Skip a little faster. Here again on the right is another, I think, bad example of solution space. It's not coming from us, it's coming from another package, which I'm not going to name, but it's not from us. And you can see there are big holes, a lot of holes everywhere. And when you browse through the solution space, you see it's really not uniform. What you want at the end is this. I mean, I think it's better for the inverse solution. You can see that the left and right points are very well balanced when you see right around the mid-sagittal plane. And globally, left and right balance is quite okay. Also, the MRI is asymmetrical here. It's an asymmetrical template. So if, for example, here there is more points on this left part, but because that's the anatomy. Another possibility for the package is to work for newborns. On the right is a newborn template. And as you know, the gray matter, the white matter is not really set up. So in this case, there is an option in Cartool to basically use the whole brain as the inverse space, but still taking care between the left and right. The monkey is back. So we can also work with monkeys. Also the same thing, you take the whole brain because the gray density is not the same as human. And the mouse is back too, taking all this solution space into the mouse brain. Still again with the same package, didn't change anything. And finally, the last geometrical problem that we have is about skull thickness. I'll go very briefly into that. The forward model needs is a local spherical model. What it says is that under each electrode, we need to evaluate basically the radii of the electrode, the radius of the outer skull, inner skull, and the radius of the brain. But basically, each time you just need to evaluate the radius of the skull. We do that by kind of probing from the electrode. We start from the surface of the electrode and we go down to the center of the brain. We compute a kind of gray distribution of this radial probe. So here it's lighter, darker, lighter, darker. So we expect the skull to be in the darker area because that's a T1. And here the skull is about here. That's bright, so that means there is fat or muscles. It's dark, so here it's the skull, and so on and so on. Lots of repetition because it's a very it's a kind of difficult to estimate because again with noisy MRIs. The other nice thing we have in the Cartool toolbox is that we use this curve which says from age 0, so newborn, to age 100 years. This curve gives us the mean skull thickness of whatever subject or patient. And this is kind of useful because you can recalibrate the estimates that have been computed beforehand. So here the toolbox, in the toolbox you can target an age. For example, the default is 30 years. And then it will adjust the conductivity and the skull thickness. Here, one or two examples which worked nicely. On the left is the MNI template. In kind of yellow is the real skull. In blue is the inner skull of Cartool detection, and the mesh is the outer part of the skull. It's a bit hard to see in 2D, but in 3D it's easier. Again, that's the same skull, just the skull with the inner skull detection, which worked pretty well when you look even below the cheek here. So the electrodes, very often we have electrodes on this part here, and the Cartool correctly back projected from the jaw up to this part of the skull, which I think is kind of neat. That's a patient or subject. No, that's a patient. How it detect. Another patient showing the inner and outer skull detection. On the left, that's a teenager, so skull is a bit different. And again, on the right it's the newborn template. I just shown the inner part of the skull. Fortunately, it worked quite well with newborn. Also, we know that the skull is very thin and even has some holes. So basically, we're here. We're good. That's just example of the final results. So that's the easy part is for template. So we work every day with templates. That I've just forgot. That's right. Still templates, but resting states data, which are a bit difficult. That's an example of the same template, the newborn template, with the mother talking to the baby. So they made some ERPs. It was Alexandra Dark at now Schneider Labs. And that was a very difficult task, because to have the baby, to record the babies. But still, I think we nailed on the auditory area. I'm not sure about that, but I think that's pretty neat. That's a side view of the same monkey, which was it was a left arm stimulation, and that's again the mouse. Unfortunately, I forgot what was the experiment. Maybe it was smelling something, and there was something back and forth within the deep structure of the mouse. Okay, conclusion. So EEG source localization is indeed a very powerful tool. It's very useful because, for example, of this time resolution, we have the time resolution that we want, for example, on the millisecond. However, we know by experience that it's very sensitive. Every step we do up until the end result, if any of these steps is failing, then you even don't know that the result is false. And as I shown these 4 steps during the presentation, basically it's about geometry, the MRI geometry, the XYZ, the electrodes geometry, solution space geometry. And it's very trivial in the sense for science researcher like you, there is nothing challenging in that. But in the engineering point of view, that you want a package that works with very difficult cases, actually it's not trivial at all to fix. And the very important thing is during these steps, it's very important that the user interact first to pilot the toolbox, and also to check all the intermediate results. And of course, Cartool is there for you. Acknowledgement. Of course, I would like to thank Professor Christophe Michel, which I've been working with for like 24 years, the time of Cartool, and of course, Professor Margita Sek and Professor Villemot at HUG, Dr. Spinelli, which I think is around here. I've been working many years with him. Professor Murray, Dimitri Van de Ville, which very often have a second look on our equations if needed. Of course, all my past and present colleagues, there are so many of them, like, I don't know, hundreds, because it's thanks to them that we tune and make the package work. And that's really a teamwork that we made in this very long run. Of course, all the CIBM staff, because that's a wonderful platform that we have here. Okay, I think I've been quite long. Sorry for the time.
Okay, no, that's great. Thank you, Denis. I thought we would see a glimpse of the software, but I guess people can access it through the website. You're welcome. There's a link actually in the CIBM website,
Yes.
so we can share that with you also. Any questions from the audience?
Yes, if I can. Do you hear me?
Yes, totally.
Yes. Hello, Denis. Thank you very much. It's very good. François, I am talking. It's very good to see how many progress you have done with Cartool, now looking at babies and monkeys. As you know, not me, but in Geneva, we really pioneered the EEG MRI combination. And I would like to know if you have done some work on that, or what is your point concerning the cleaning and filtering of the EEG and problem related to the combination of both modalities?
Yeah, that's a good question. That's a good question. Actually, not really. Actually, I think that was last year. I was talking with Frédéric Grouillet, yeah. And suddenly in my head, I was like, okay, that's no big deal. Just filter this data and stuff like that. And just by talking with him like 15 minutes, I just realized like it's a really tough. It's a tough subject. So since then, I just realized that if we want to address this issue of the MRI contamination in the EEG, it really needs like a real focus on that. So I don't know if there is enough demand on this subject. I will be totally happy to focus on that, of course. But right now, there is nothing to be that have been done on this specific part.
And another question, in the same line a little bit. What about the subdural or implanted electrodes?
Mm-hmm.
Do you have solution on that, or it's not worth looking at that? You know, either grids or implanted electrode, I don't know.
What would be the issue? I mean,
yeah, for instance, you know, if, for instance, you may think that a grid or electrodes are not exactly on the target or on the epileptic focus, whatever that you target. So it means that there is perhaps also a need to better localize the
yes,
based on intracranial recording.
You want to improve the intracranial localization, you mean?
Yes.
Didn't thought about that. What we've been working since 1 year with the HUG, with Marc Guidasek and Serge Villemot, is actually to have better localization with without electrodes. So just from the inverse itself, to try to improve the localization of the epileptic spike. But with a grid itself, I don't see. Yeah, I'm not right now. I don't see how much we can improve once you've got the grid inside the brain.
Yes, it's supposed to be on the right place. Yes.
Yeah.
Any other questions?
Hi. Can I ask a question?
Yeah, totally.
Yeah. So thanks a lot for the presentation. So I used to work with EEG, now I'm working with MRI, and I was wondering if it's possible, for example, because you were having some problems with newborn with the solution points. instead of using only the gray matter, you were using the whole brain. So there is a chance to introduce for example, the gray matter segmentation as a mask, for example, to select the solution points. Or there is a way in Cartool as well, for example, for adults, for healthy brains, that to introduce or the surface, for example, to just restrict the solution in the cortical surface.
Yeah, totally. Yeah, the package can accept any gray mask you want and any solution points that you design. The default is to go through the predefined pipeline of Cartool, but in between this pipeline, you can plug yourself with whatever you pre-processed, the MRI pre-processing, and of course the solution points. So you can give whatever solution points you want, but I assume also that people doing that, so they kind of shortcuts the pipeline. Usually they are experts, they know what they're doing. Because if you, for example, if you ruin the left and right balance, then you also have a problem, because all if there are more solution points on one side of the brain, all the inverse solution will be on this side, of course. But other than that, yes, the user can plug any solution point he or she wants.
Right, thanks.
Yeah.
I got a question as well.
Yeah.
First of all, thank you for the presentation. I've been using M&E on Python a little bit, and in their pipeline, I believe for source localization, the source space used is a surface source space placed on the surface of the white matter mostly.
Mm-hmm.
So they don't use as much volumetric sources spacing as you showed in your presentation. What do you think about surface grid, and how do you think they compare to volumetric grid as you shown in your pipeline?
So you mean surface? You mean really on
the surface of the white matter?
Of the gray matter?
Of the white matter, yeah, I think.
The white matter?
Yeah. I think that's what they're using mostly in the mainstream pipeline. Mm-hmm. So yeah, since both pipelines differ and the default differs between Cartool and M&E, I was wondering what you think about this alternative.
So you say on the surface of the white matter?
Yes, I think that's the default.
Yeah. But it still follows the
yes.
surface of the brain.
Yeah.
Okay, yes, I see. You know, I'm not sure. I mean, I haven't experimented, but I'm not sure it will really make a real difference between the gray on the surface of the white matter. We picked the gray matter because that's where the sources are supposed to be. And but given the resolution of the final inverse solution, let's say approximately say 1 centimeter. So I think you will catch up what is within a 1 centimeter cubic volume.
Okay.
Or is it really different? It will be interesting still to compute the 3 variant. I would say the gray mask of Cartool. I say a mask because it's quite thick. The one that you're talking about, and the third one would be like the whole brain, except the CSF, of course, and
yes.
to see what's happening. Yeah, that would be interesting.
Okay, thanks.
Yeah, you're welcome.
Any other questions? No? Thank you again, Denis.